All right. Hey, everybody. So I just wanted to go over this real quick. I think the history stuff is pretty well covered in the videos I posted already that are done by other people. And it'll give you either an appreciation or a respect for what I don't do. So there you have it. But this is where we ended up, basically where I wanted to start, because this isn't like everyone else. We followed with the history of the atom, this road that we were pretty sure was on solid ground. We actually thought that we had nothing but a ball under us. Wait, where'd it go? There it is. Right, that's sort of where Democritus and Dalton were. Was that you were just standing on top of a lot of well, well established base filling models. And it turns out that the more we learned, that there's really very little to an atom, a lot of empty space. And somehow, and it's still a bit, it's actually very higher thinking as to how it is you don't fall through the floor with so much empty space and the atoms in between, and even that the atoms that make you up, etc. Anyway, the point is we learn from our history, and that it helps us understand that history, that we're in the middle of history right now, that what we know now is not necessarily true. So that's what we know so far. That's pretty much self-explanatory. We know that a revision to Dalton's theory was that there are subatomic particles. The nucleus has the neutrons and the protons in it, and the electrons fly around. And we talked about this model and how there are a couple things wrong with this model. One, that electrons don't really follow orbits, and two, that the empty space is really not very appreciative here. That if you put a grape, or I even read recently, a grain of rice in a stadium, like I said RBC, but I guess it's called PNC Arena now, that if the nucleus were the grape, then the electrons would be flying around to the outer regions of the stadium. So it is a lot of empty space in an atom, and that, yeah, electrons aren't really orbiting. They're sort of running around like preschoolers without any real direction. All right, so we talked about the atomic mass unit. The atomic mass unit, if you convert it to kilograms, is a very, very small number. So we just invented, as we meaning scientists, this atomic mass unit where a proton and a neutron were about one each. And you can see here that the electrons are actually much, much smaller. So even though they have mass, there's definitely mass to an electron. It's not significant compared to the proton and neutron, so it is sort of disregarded in the mass of an atom. However, it's not to say it doesn't have mass. The charges, however, the proton is a +1 charge, and the electron has a -1 charge, and the neutron is neutral with no charge. So the proton has both a plus charge and a mass number. The neutron only has mass, and the electron only has a charge. All right. So, and we discussed real quickly how electrons can be attracted and yet not crash into the nucleus. And that again is answered in one of those videos as well, that basically it's moving around so fast that the attraction just keeps it from flying off of the radar. But anyway, atomic number, they gave that the annotation of a Z, which is the number of protons in an element, and this is what defines the element. Every carbon has 6 protons. If you add a proton to carbon, it is no longer carbon, it's going to be nitrogen, and so forth like that. The mass number has the letter A, even though atomic number starts with A, they gave mass number the A, and nothing has a Z in it, so for some reason atomic number got Z. But the mass number is the sum of the neutrons and protons. Based on your quizzes, this is pretty well understood by most. And the ionic charge is due to electrons gained or lost. We are punting on this right now, just letting you think that protons equal electrons unless an ionic charge is stated. I am not stating ionic charges this time around. We'll wait until the next unit to really understand why that happens before we start talking about how electrons are gained or lost. All right, so this notation that everyone gets upset about because it's upside down versus a periodic table, you put the mass on top and the atomic number on the bottom. So the number of protons goes on the bottom, and the mass, the protons plus neutrons, goes on the top. And, keep in mind, this is for one atom, not a group of atoms. So there might not be, so if we had C14, for example, where the protons would be 6 and the Do I have that example? I have that example here. That's an isotope of carbon. The neutrons might be 8 and the protons are 6. So even if you look on the periodic table, there is no 14 for carbon. That just means that one atom has the mass of 14. So Dalton thought all atoms were exactly alike. That's not true. They're only alike in their protons. Isotopes have the same number of protons but different neutrons, and ions have the same number of protons but different electrons. Keep in mind, protons define your element. So there it is on the periodic table. You have your atomic number always visible, and then the average atomic mass. That's why it's not a whole number. It's always going to be some strange decimal, and that's because we take the average of all the atoms and all the isotopes of that element. So fluorine here would have an atomic number of 9, and the mass would be 18.998. So we got this down pretty good here. So element name mass number is what we call mass number notation. Since the element tells you how many protons there are, you know carbon has 6, and then all it tells you is the mass, so you know that the neutrons are 14 minus 6, which is 8. Hydrogen 3, hydrogen tells you it has 1 proton. The 3 tells you the mass is 3, so 3 minus 1 means there are 2 neutrons. So there you have it. So here's an example of isotopes, and it's key to remember that isotopes act just like the element. People seem to be thrown off by the fact that there are some radioactive isotopes. Well, that's true. They're unstable nuclei. However, they still do all the things that, in this case, hydrogen would do. So this tritium is radioactive. But if you make water out of it, it still looks like water. It would still taste like water. It would just be slightly radioactive water. So neutrons can contribute to an atom's stability. Many isotopes are radioactive but react the same. That's the key here. Deuterium is a more prevalent isotope of hydrogen. It is not radioactive. It just has 1 neutron and 1 proton. So there's that. All right, and these are some examples of radioactive isotopes and what we do with them. You're not going to have to know these. I was trying to tell you about the carbon dioxide that they made with carbon-14, and this acted just like carbon dioxide. It got sucked up by a tree, as you would expect carbon dioxide would. It got converted to sugar in the tree, just as you would expect carbon from carbon dioxide would, but it was radioactive, so it sort of gave this signature of radioactivity, and it helped people understand that once every tree in a forest was radioactive after just subjecting one tree to this treatment of carbon dioxide that was radio-labeled, that there is an underground network where all trees share. It's not just birches share with birches and firs share with firs. All trees are sharing. All right, more examples. Magnesium 26 would have 12 protons by definition. That's what magnesium has. Since we know the mass is 26, it's 26 minus 12, 14 neutrons, and we're going to just say electrons are the same as protons for the rest of this unit. Chlorine 34 would have 1 atom of chlorine, which has 17 protons. The mass is 34. So 34 minus 17, that's telling you there's 17 neutrons and 17 electrons. So what is the atomic number and mass number of an element that has 10 protons and 11 neutrons? So the atomic number would be 10. The mass number would be 10 plus 11, or 21. All right, so that would be neon 21, or neon in this way. All right, isotopes, same number of protons, different mass. Carbon 12. Yeah, that's all right. We don't need to go through this. You all got that pretty down. All right, then we got into an average atomic mass, and that's the weighted average of the atomic masses of naturally occurring isotopes of an element. We did this nice serial experiment where we had Golden Crisp and Kix, and we compared the masses of them and how you would have one isotope and another isotope of an element, and you would just multiply the percent of that isotope in the example of atoms that you would have and the percent of the other isotope. So here's an example. Chlorine has 2 principal stable isotopes. Chlorine 35, which accounts for 75.78% of all chlorine atoms, and then chlorine 37, which accounts for 24.22% of all chlorine atoms. So what is the average atomic mass, or what would we put on the periodic table for the mass of chlorine? Well, the 35, even though it's 34.969, we're going to call it 35, and we're going to multiply it by this percentage. The percent can be expressed as a decimal, so 0.7578 is 75.78%. 75.78 divided by 100 gives you 0.7578. We're going to add that to the other isotope, this chlorine-37, times its percent, 0.2422. 35 times 0.7578 is 26.52. 37 times 0.2422 is 8.96. You add those up, you get 35.48, which should be close to what's on the periodic table, and it represents sort of an overall mass. And here you can see the relative abundance when shot on a mass spec. There's about a 3-to-1 ratio of when chlorine gas is shot, that there's more chlorine-35 than there is chlorine-37. All right, so bromine was another one. It comprises of a bromine 79, which is 50% about, and then 81, which is the rest, which is 100 minus 50.54, so that's 49.46. So it's pretty much a 1-to-1 relationship with a slight advantage to 79. So you take the mass of the 79, multiply it by the percentage, add it to the mass of the bromine 81, times the percentage for that, and you get 79.98. So as you can see, slightly favoring 79 versus 81. It's a little bit on the 79 side of things versus the 81 side of things, because there's a slight larger amount of 79 to 81. All right, here you can see with that mass spec that the bromine peaks are about the same height. When you have something with bromine in it, you're going to have something separated by 2 like that, because there's the same abundance about of each. All right, so that is that. And then very quickly, I just wanted to go through what we did today. Today we had a big mole party. We started with cereal, and I defined a bowl as 175 pieces of cereal. Now, if there's 175 Cheerios or 175 mini wheats or 175 Rice Krispies, those look very differently because of the size of the cereal, right? This and this and this all have 175 pieces in it, but because of the size and shape of these cereals, they're going to have different appearances and different masses. So if I just asked you how many pieces would there be if I define one bowl as 175 pieces, 2 bowls of cereal, you would figure that out by saying 2 bowls times 175 pieces in one bowl. That's your equivalent that you can cross off bowls. 2 times 175 leaves 350 pieces would be available in 2 bowls. So that here and this here have 350 pieces, even though they look very differently. But the mass would be significantly different. The Cheerios versus the mini wheats versus the Rice Krispies would not have the same mass. And that's the same with elements and atoms of the mole. So just to stress that mass again, so 1 bowl of Cheerios is 30 grams. How many grams would you have in 4 bowls? Well, since we know 30 grams is 1 bowl and we have 4 bowls, we want to cancel out the bowl of Cheerios. So when we do set up our dimensional analysis, we want bowls in the bottom and we want grams on the top. And that's the relationship right here. 1 bowl is 30 grams. So 1 bowl is 30 grams. 4 times 30 is 120 grams. All right, same is true for a mole. What is a mole? Well, a mole is a big, huge number that allows atoms to be measured up as grams. And how many atoms are there? There are 6.02 times 10 to the 23rd atoms. And if we had grains of sand in that same amount, 6.02 times 10 to the 23rd, you could build a structure that's much bigger than the football stadium where the Houston Texans play football. All right, so what is a mole? Since the periodic table has an atomic mass unit, 1 mole of atoms converts all that to grams. 1 mole is 6.02 times 10 to the 23rd particles. Often it's said it's like a dozen. If you have 12 donuts or 12 bagels, those are both a dozen. If you have a mole of donuts, you would have 6.02 times 10 to the 23rd donuts. If you had a mole of bagels, you would have 6.02 times 10 to the 23rd bagels. It is a number. It's known as Avogadro's number because Amedeo Avagadro was the one who came up with it. Here's his picture. He's famous for, among other things, being on Trader Joe's avocados number guacamole. It's got the mole and it's got sort of Avogadro, avocado play on word. So molar mass in grams comes from the periodic table. So, oh boy, here we go. So, if you want to know how much 1 carbon atom weighs or what the mass of 1 carbon atom is, you look on the periodic table and you see that it's 12.011 AMU. That'll be on the periodic table there. Not the worst thing I've done. 1 mole of carbon would have 6.02 times 10 to the 23rd atoms in it. 6.02, oh boy, times 10 to the 23rd. There we go. All right. So that's how many atoms there are. And if you want to know how many grams it is to have a mole of carbon, it's the same number on the periodic table. Instead of AMU, though, it's in grams. So that's 12.011 grams. 011, that would be a 0. So sulfur, if you look on the periodic table, it's number 16, I believe, and atomic mass units would be 32.0 something, I think 06. Let's say that. But that should be the mass from the periodic table, and that's how many atomic mass units one atom of sulfur would weigh. If you had a mole of sulfur, it would be the same 6.02 times 10 to the 23rd atoms. And it would be the same as the AMU, only in grams. So if you had a mole of sulfur, zeros always have been my downfall. If you have a mole of sulfur, it would weigh this amount in grams, so it would be 32.06. So what Amadeo Avogadro did was turn all of the periodic table into grams by figuring out how many atoms were needed to make everything on the periodic table be a gram. And believe it or not, that says 32.06. Let's hope that's right. All right, so we did some mole conversions. How many grams are in 0.275 moles of silver? Well, we're starting with 0.275 moles, and we want to go to grams. So we are going to want to use, and I apologize for this, this should be better. We want to go to grams. So the two things we know about silver is that 1 mole equals 6.02 times 10 to the 23rd. Oops, equals 6.02 times 10 to the 23rd. And that's atoms. So that's a helpful thing, but not for this case because we're looking for grams, not atoms. So that would be helpful if we were looking for atoms, but we're not. So the other thing is what we're going to look for. I apologize for that writing, but 1 mole is equal to 107, which is the mass from the periodic table, equals 107 grams. 7 grams. I don't know if this really helps to have these. All right, so I need a better pen. So we're going to use this one. Hold on a second. Let me see if I can get an eraser. Ooh, look at that, an eraser. That went over a little too far. All right, hold on a second. Back to the pen. 107 grams. There we go. This came from the periodic table. Since we're going from moles to grams, that's the one we're going to want to use because we want to cancel the moles and we want to go to grams. So that is the equivalent. That is the relationship we're looking for. There, now that looks like a G. So it's 107 grams with 1 mole. And then you multiply 0.275 times 107 and you get the answer. You get the answer of, sorry that happened, but it did, 0.275 times 0.275 times 107, and you get an answer of about 29.4 grams. All right, so then we did another one with this. Now you're going to be using the 1 mole equals 6.02 times 10 to the 23rd atoms as your equivalent. And just come see me if you want me to do this out, because I don't want this to bore everybody with this video. But you're canceling atoms and you're going to moles. I guess I am going to do it, aren't I? I'm going to do it. So we're canceling atoms, going to moles. Pen. So 3.89 atoms, 0.89. Maybe I shouldn't have done this. Times 10 to the 26th. Times 10 to the 26th. Makes you appreciate what Khan Academy does, though, huh? 26. That is atoms. And we want to go to moles. So to go from atoms to moles, we need to cancel atoms and have moles on top. And so that's why we're going to use not the periodic table relationship, but the atom relationship, which is 1 mole in 6.02 times 10 to the 23rd atoms. 1 mole is 6.02 times 10 to the 23rd. All right, this is so exciting. So you're going to divide 3.89 times 10 to the 26 by 6.02 times 10 to the 23rd, and you get something like 600 and something. I don't remember. But make sure you know how to do that on your calculator. It's like 600 and I have a calculator on my phone. You don't have to see me lose everything. There it is. All right, so it's 646, I believe. 646. 646 moles. So make sure you can do that. I'm going to stop this video before I lose my license on YouTube. Good work, kids. We can talk more tomorrow about the mole, but thank you for listening.